58E. In order to summarize my presentation, I will first go over the first observation of exchange bias systems and measurement techniques of exchange bias, then materials that show exchange bias characteristics. After that, materials which affect parameters which affect exchange bias and theoretical models which explain them. And for last, I will go over the applications of exchange bias. First observation of the exchange bias systems. The magnetic properties of antiferromagnetic materials wasn't the industrial interest of our humanity until 1956, as I wrote here. In 1956, Michael John and Bean observed oxidized cobalt, the exchange bias properties. They first observed the horizontal shift in the hysteresis loop of cobalt, and they also observed the increase in the coercive field of the cobalt material. After this observation, they look into the material and I see that their cobalt is oxidized. This also the cobalt oxide has antiferromagnetic characteristics. What do they observe extra to the increase in the coercive field and shift of the hysteresis loops? The shift of the hysteresis loop, which the center of the hysteresis loop movement is donated by the H sub EB, which donated as the exchange bias, which I will use in my presentation. They also observed the non-vanishing rotational hysteresis loop. They start to rotate the ferromagnetic layer, but while they're coming back, they see that they don't go over the same line. And also they see that unidirectional anisotropy here, because uniaxial anisotropy has two minimas, which is pi degree apart. But as you can see, we have one minima here, which donates a unidirectional anisotropy in our material, which comes from the sum phi component in the energy term. Uniaxial anisotropy, contrary, donated as the sine square phi component. And also, their observation vanishes after the Neel temperature of our antiferromagnetic layer, but they experience these loops in below the Neel temperature. After the Neel temperature, our antiferromagnetic layer just adds a paramagnetic characteristic to our ferromagnetic layer's hysteresis loop. In first times, how do they explain this phenomena? They first tried to explain this with a energy term, surface energy term per area. As you can see, this first term donates the interaction between applied fields and our ferromagnets. Second term adds the anisotropy energy of our ferromagnets. Second term adds anisotropy energy of our antiferromagnet, and last term adds the interaction energy between ferromagnetic and antiferromagnetic layers. As you can see, the process summarized here. You cool the material above the Neel temperature but below the Curie temperature to a temperature both below the Neel and Curie temperatures to observe exchange bias. After that, when you start to apply field, you cannot turn this material to the opposite direction because of the interaction between this antiferromagnetic and ferromagnetic layers. When you turn that, this antiferromagnetic layers just shifted a little bit, but ferromagnetic layers pointing the opposite direction. While you are turning the original direction, it is easier to turn back. The energy equation has angles, which is presented here. The alpha is the angle between magnetization of antiferromagnet and anisotropy direction of antiferromagnet. And also in this equation, anisotropy directions of ferromagnet and antiferromagnet assumed to be parallel, and beta is the direction between magnetization of ferromagnet and anisotropies, and theta is angle between applied field and the anisotropy directions. What do this equation missing? It's missing something, so we try to improve it in later on. It's missing the domain energies and domain formations, and it's also missing the non-parallel condition of anisotropies. As we observed in other materials, not cobalt oxide, but other formations in thin films, we may have non-parallel anisotropies in our bilayer system. But if you want to talk about this energy and we want to show the characteristics from this equation, this ferromagnetic anisotropy is in experimental part is smaller than the antiferromagnetic anisotropy and other terms. So if we neglect this ferromagnetic anisotropy term and try to minimize this, if this condition, anisotropy of the antiferromagnet, dominates the interaction energy, we can have exchange bias condition, which is denoted as the exchange bias given as the interaction value thickness and magnetization of interaction divided by magnetization of the ferromagnet. But if this condition is not does not exist, our antiferromagnetic layer starts to turn with the ferromagnetic layer, so just adds a paramagnetic behavior to our material. Cannot stabilize our bilayer system. How we can measure this effect? First, we can use magnetization, magnetizing a material, and then, magnetizing a material and then observing the exchange field and coercive field is the mainly used technique for our materials. To do this, we can use a couple of systems, materials, or something like that. For mostly used things are listed below. SQIDS is really helpful to magnetize our materials and see hysteresis loops. Also, Kerr effect, which depends on the polarization of photons, is a useful tool to measure hysteresis loops. VSM and loop tracers are also can be used. Also, we can use the torque measurements as I told before. This rotational hysteresis also exists in single ferromagnetic layers. But in single ferromagnetic materials, this hysteresis loop only exists in the small applied field regions. But as Michael, John, and Bean observed, this rotational hysteresis is non-vanishing characteristics of exchange bias. We can have rotational hysteresis even in large applied fields in our ferromagnetic or ferromagnetic and ferromagnetic bilayer system. Ferromagnetic resonance, which Ege will talk in following week about, is also a technique to measure exchange bias characteristics of our system. In FMR, samples mounted in microwave cavity are subjected to high frequency magnetic field with a DC field inside. And with sweeping the frequency of the applied AC field, we observe the resonance frequency of the spin waves. And from the resonance frequency of the spin waves, we can derive the stiffness of our material, so we can see the exchange bias characteristics. Neutron diffraction is kind of a more useful thing to observe exchange bias and exchange bias systems, because neutron diffractions gives us ability to observe the thickness of the material. With neutron diffraction, we can observe the thickness and domain formations in our materials up to 2 nanometer resolutions. But contrary to other effects found by other effects, neutron diffractions experiments, as far as I can see, gives no domain formation or inhomogeneity in the FM layers, FM or AFM layers. But ferromagnetic resonance, and as we will talk about other techniques, gives inhomogeneity in ferromagnetic layers. But this inhomogeneities and domain formations observed in higher fields than simple ferromagnetic layers because of the effect of the antiferromagnetic layers on the ferromagnetic layer. Magnetoresistance curves, AC susceptibility, and domain observations can also be used in our exchange bias systems. Sorry, I will explain them just now. And magnetoresistance curve, as can be observed in magnetic tunnel junctions, can be shown here, is useful technique to observe our exchange bias systems. From this magnetic tunnel junction with applied current and field, we can see a hysteresis loop just here and here, something like hysteresis loop, with just gives the dependence of R to applied field and magnetization to applied field, gives us the ability to calculate the coercive field and exchange field of our fixed layer. This FM, AFM materials are used as fixed layer in spin-torque oscillators, spin-on oscillators, in out-of-state technologies. AC susceptibility. In AC susceptibility, the change in the magnetic flux created by the sample due to the presence of the alternating field is measured as a function of the applied field and sometimes as a function of the temperature even. The results in the AC susceptibility gives more detailed information than the DC measurements as we talked before, like magnetization or so. And AC measurements indicate that FM layers form inhomogeneities in thickness. Domain observations, as I said before, gives additional energy terms in previously donated energy equation. This can be observed with Kerr effect, which we talked before in magnetization, and Bitter method, as we learned in physics 58E class, and Lorentz microscopy. The Lorentz microscopy is shown here. I had the photograph of it. Different magnetic portions in material create diffractions, and thanks to that we can observe the materials domains which have different magnetization inside them. Other techniques are brilliant scattering, magnetic discursion, and Mös-Bauer effect. Brilliant scattering. In brilliant scattering, samples are irradiated with a laser beam in visible range. With the scattered light as a function of the material structure and the depth or other characteristics, we can indicate the inhomogeneities in the FM layer. Magnetic discorism. In this method, electrons in the material excited with the X-rays, and the photons emitted from the material measured as a function of applied field and also as a function of temperature. High sensitivity different. This method has high sensitivity to different material types. So this gives us ability to differently study material dependent characteristics of our material and studies of depth also. And with this method, we can also study the buried layers or interface of our material. Mös-Bauer effect. In this effect, AFM or FM layers, in one of the components of this material, it can be also in the AFM or FM material, is change with its radioactive isotope. From this radioactive isotope, we can observe the radiated gamma rays, and so we can predict the characteristic of this location. This really depends on where you put the radioactive material, so we can observe different parts of our material. So thanks to that effect, also we can observe the domain characteristics or domain formations depending on where we put our radioactive isotopes. Now I will talk about the materials that show exchange bias characteristics. As small particles are the which exchange bias first observed. But these particles are relatively difficult to observe and study exchange bias because these small particles are really dependent on the growth characteristics, and they are really easily broken or lose their characteristic behavior depending on oxidation state or grain formation inside them. We cannot control them relatively good or control their behavior. We cannot just stabilize one characteristics and stay the others same. So they are not our favorite particles to study exchange bias today, but they are the first particles which give exchange bias characteristic first. Also, we have inhomogeneous materials. Inhomogeneous materials, while I'm saying that, I refer to the multiple layered materials or random located antiferromagnetic and ferromagnetic systems like Thomson's cake, I say. These materials are also not easy to study because while you cannot measure the position of antiferromagnet and ferromagnet, also you cannot relatively good measure the surface area of the antiferromagnet, and materials such as you put can oxidize in the grains and grain boundaries, which increase the efficient area of the ferromagnet and antiferromagnet, which gives rise. We cannot control them. So they are also not really good to observe exchange bias. Scientists, after observing these two systems, come to a third one, coated antiferromagnetic single crystal. What's coated antiferromagnetic single crystal? Antiferromagnet coated in a single structure plane to give homogeneous characteristics, and after that, it's covered with ferromagnetic material. But contrary to what's expected from this method, this coated antiferromagnetic single crystal types give less exchange bias characteristic than the previous small particle and inhomogeneous materials, counterparts of them. This can be because of the uncompensated and compensated surface spins, which can be shown here. This is referred as the uncompensated spins of surface. This is compensated. In compensated case, we do not have a net spin pointing to one direction. They are countering each other. In uncompensated case, we have net spin moment pointing one direction. Also, in today's technology, we mostly work on thin films when we call exchange bias. Thin films are relatively easy to observe just one effect and put others same to one condition. And also they are easy to manufacture relative to the others because others manufacturing process also depends on the material or small effects, like I told, the grain oxidation or so. In thin films, we have a couple of AFM types, oxide AFMs, metallic AFMs, other AFM types, other than these ones, and ferromagnetic materials. Oxide AFMs are the first one observed, as I told, cobalt and cobalt oxide. However, this kind of samples are difficult to compare. This oxide layer can be measured quite accurately. The films may tend to oxidize through the grains again, thus increasing the interface surface. However, this oxide is usually polycrystalline, and sometimes they have multiple phases. For metallic antiferromagnets, they are first introduced in 1964, and they are used today's technology too, as a iron manganese or iron nickel. In first reported metallic AFM is iron nickel manganese bilayer, which has blocking temperature at 300 Kelvin. It's relatively high compared to that time's technology. And other AFMs includes non-oxides and non-metallics like nitrides, fluorides, and sulfides. They are also hard to measure, like in oxide case, because of the grains and other characteristics. Ferromagnetics, several systems which have a ferromagnetic part as reported in studies. Ferromagnetic materials can be used in both for ferromagnet part and both for antiferromagnet part because of their characteristics. They can play either role. A system containing ferromagnets in at least one of their components are difficult to analyze theoretically because ferromagnet characteristics give difficulty in theoretical explanation in equations. But also ferromagnets can be both sides. Ferromagnet systems are also observed and reported in experiments. For parameters which affect exchange bias and theoretical models which explain them. Training effect is highly reported case. As you can see on the left, we have three types of training effects. We have three types of training effects: type 1, type 2, and type 0. Type 0 is something like middle of the type 1 and type 2. Exchange field depends on number of the consecutive hysteresis loop measurements performed. This is called the training effect. This property first observed by the and his collaborators in 1966. And theoretical model explain this experimental result done by the Dr. Zhang and his collaborators. First type of training effect, as you do the consecutive loop measurements, this hysteresis loop begins to shrink in both sides. In second type of training effect, as you do the consecutive loop measurements, hysteresis loop in two branch of the hysteresis loops try to shift to the light, become to shift to the right. In type 0 case is something like the middle left part of the hysteresis loop goes to the right and left part is stable. Experimentally observed characteristics of training effect can be shown in this equation, simple equation. A change in the exchange field is proportional to 1 over square root of n. N is the consecutive loop number. And this is the explanation of the theoretical model. Dr. Zhang said that he explained the situation by ferromagnetic and antiferromagnetic coupling inside the antiferromagnetic layer. it is suggested, according to Nice suggestion, they introduced the direct exchange coupling between the AFM grains. As an example, a negative coupling may exist between the AFM grains whose sublattice match each other, but the net surface, as you can see from the left part of this photograph, they match each other, but the net surface spins are antiparallel. And this type of this part of the antiferromagnetic layer shows negative coupling, and other part they are also coupled, but surfaces are parallel. They show positive coupling. With this assumption, Dr. Zhang achieved an explanation for the straining effect. Another effect that affects the exchange characteristic of our materials are uncompensated interfacial spin model. Exchange bias generally in theoretical models and experiments depends grain size. Exchange field is proportional to 1 over L, which L denotes the grain diameter, average grain diameter. As you see on the first photograph, this bottom part denotes the AFM interface, and the first part, A, has a fully compensated AFM surface. Because of this fully compensated AFM surface, we do not see any vertical shift in our hysteresis loop. But if we have uncompensated AFM surface, depending on the interaction between the AFM and FM surfaces, we may have upwards or downwards shifts in our hysteresis loops. If we have ferromagnetic interaction between the AFM and FM surfaces and also uncompensated surface, we observe upward shift in our hysteresis loops. If we have antiferromagnetic interaction, we observe downward shift in our hysteresis loops. And the D part explains some experimental different findings in papers. Even if we think we have fully compensated surface, we may have some grain-bound grains which have net uncompensated spins in them. So even if we think that we have a compensated surface, we may have shifts in our samples. And this is also found, and also explained by Dr. Takano and his collaborators. They also say that these uncompensated spins can be created because of the non-parallel surface normal with lattice plane. This angle can create these uncompensated surfaces, and they also found this equation, which is exchange bias proportional to the 1 over grain diameter in theoretically. We have other parameters which affect exchange bias. Thickness dependence. We may change two thicknesses, FM or AFM. Dependence of the exchange bias to FM thickness can be given by this equation in non-so-thin FM layers, because if you make your FM layer so thin, it can be discontinuous, so it loses these characteristics. But after a certain thickness, we can explain this characteristic with this equation: exchange bias field proportional to 1 over thickness of the ferromagnetic layer. But thickness of the antiferromagnetic layer is something more complex. In generally, after a certain thickness of AFM layer, exchange bias is independent of the AFM layer, which this thickness depends on the system, but it's something like in the range 20 to 40 angstroms. After if you go below this thickness, exchange field decrease drastically. You see this part, which it decreased drastically. It can be because that, as we explained, this exchange bias characteristic, I told that the anisotropy part that comes to energy must be bigger than the interaction part of the energy. When you decrease thickness of the AFM, you may lose this equation. So AFM may start to rotate with the ferromagnetic layer. And also coercive field shows a different characteristics with changing thickness of the AFM layer. It decreases with increasing thickness of the AFM layer because this in generally, but after a point start to decrease the thickness of the AFM, it shows a peak and decrease drastically like in the exchange field. Because after some point I said that the exchange interaction is lost. And also out of plane AFM spins may affect the exchange characteristics. What if we have all spins of the antiferromagnetic layer out of plane? There are two types of theories which can explain that. In both theories, both theories give the same correct result. In one type of theories, this interaction may depend on the average spins dot producted, which gives a cosine term. And this cosine term, when AFM spins are out of plane, gives 0. So out of plane do not have any exchange bias contribution. And in other type of theories, exchange bias field is proportional to square root of effective anisotropy times effective stiffness. In out of plane case, which is equal to the square root of the AFM anisotropy and AFM stiffness times cosine alpha, which is again gives 0 in out of plane case. Interface disorders may also change the exchange bias characteristic. First interface disorder comes to mind is roughness. How roughness changed the exchange bias characteristics? As roughness increases, generally exchange bias is decreasing, which can be easily understood in uncompensated case, but in compensated case, it is not really easy to understand the roughness change in exchange bias energy. Crystallinity also affects exchange bias, as if AFM spins are oriented in single direction. This increasing crystallinity increases the exchange field. Also, grain size, as we showed before, is a part of interface disorder and affects the exchange bias field. Interface impurity layers added to the exchange bias material may also affect the exchange characteristic, but it's not like it's not show the predicted characteristics. Couple of impurity layers is not enough to destroy the exchange characteristic of materials. Some nanometers of material must be added to completely destroy the exchange bias characteristics. Also, anisotropy, blocking temperature, and cooling field may also have effect on the exchange bias characteristic of materials. Increasing anisotropy, basically in antiferromagnets, increases the exchange bias characteristic of materials, as shown in the previous theoretical models. All models predicted that before. Blocking temperature is the temperature which exchange bias field does not observe. In blocking temperature depends on the thickness of materials, AFM thickness or FM thickness. As you make your material thinner, this blocking temperature decreases, because if you make our material bigger as a whole, as expected, it must be a nil temperature. But if you make it smaller and thinner, it will decrease. And cooling field in generally does not affect the exchange bias field, but in some materials, iron difluoride, for example, exchange field has really important. Exchange field is really important. When you increase the exchange field in, for example, iron difluoride, after a certain point, if you keep on increasing the cooling field, iron fluorides start to show positive exchange fields. What I mean by positive field, in generally, exchange field, as we saw on the graphs, is negative to the applied H field. But after a certain range, increasing cooling field may cause a positive shift to the right side exchange fields in, for example, iron difluoride. Applications of exchange bias is really broad in industry. And simple example of that, exchange bias materials can be used in the read and write heads of the hard disks, which increase the density that we can store data in our daily use or industrial use. And also, exchange bias materials are used in the out-of-state technologies like magnetic tunnel ejection and spin-torque nanooscillators, spinol nanooscillators. All of these materials has fixed layers inside them, which is just the exchange bias system with ferromagnetic and antiferromagnetic bilayer system. Thank you for listening. These are the basic references I used in my presentation. Thank you all.